Okay, great.
And the audio is on, so if someone talks, we can hear them, but it should be fine.
So we'll go ahead and get started. So welcome to all of you this afternoon. Our speaker this afternoon is Jason Turner. He's coming from the University of Arizona, where he's a professor of philosophy. Jason received his PhD from Rutgers, and he's taught at the University of Leeds and St. Louis University. He's published on a wide range of topics in metaphysics, ontology, meta-ontology, and their intersections with broadly logical notions and issues. And he has a 2016 book with OUP, The Facts in Logical Space. Talking with him this afternoon, I learned that what interests him is not so much arguing for an overall philosophical view, but rather seeing structures and how they show up in particular problems. He writes on his webpage that he is secretly interested in everything, and that he will probably continue to dabble until someone makes him stop. And his talk today is proof that he's secretly interested in everything. It turns out that he also has a fondness for aerospace engineering. Thanks to Joshua for helping me find the right word for that. I was like, aeronautical engineering? No, that doesn't cover rockets. It's aerospace engineering. So the title of his talk this afternoon is How to Send a Rocket into Orbit Without Numbers. Please join me in welcoming Jason.
Thank you for the introduction and for having me out. I'm delighted to be here. Before I begin, as I was preparing this, after I had already sent the title and abstract, I realized it's a little more technical than I was I thought in my mind when I was choosing what I was going to talk about. So I know there'll be, of course, the Q&A later, but if there's any just purely clarificatory questions, if something is going by too fast, I'm not quite tracking some of the technical aspects, feel free to raise a hand in the middle of the talk, and I can interrupt and I can try to clarify things. And if it looks like we're veering into more Q&A kind of philosophical material, maybe we'll mention that and we'll then move back, but just to make sure that we can all be on the same page. Because nothing is going to be gained if I just talk too fast and we don't know what I'm talking about. And nobody gains that way. So anyway, what I want to talk about today is part of a broader project that I'm interested in, which the broader project is the metaphysics of science. But this particular issue is one that arises in the metaphysics of quantities. And by a quantity, I mean the kind of property that we typically refer to or pick out with a number attached to a unit. And this is not a definition, this is just a characterization to kind of get you on the sort of thing we're talking about, but something like 25 kilograms in mass, or 7 feet in length, or 60 seconds of time, those kinds of properties I'm talking about. And what I want to do is I want to start by sketching a view that I find very attractive, a number of people have found very attractive in the metaphysics of quantities, and then describing a problem that arises for that view, and then attempting to solve that problem. That's structure. This is going to be a problem solution style presentation. That's the hope. The view that I want to sketch is one that is called representationalism. There is it's a broad family of views. There's lots of details, ways that different representationalists can disagree amongst themselves about things, but the basic spirit of the view is summarized nicely by a quote from Bob Stalnaker, in which he's actually just describing this to compare it with something else, not even his point, but it's a nice kind of description that's here in your handout. So he says, what is it about such physical properties like having a certain height or weight to make it correct to represent them as relation between the thing to which the property described in a number? So, for example, what makes it correct to say that I don't know, my mass is in kilograms, so I'm going to make something up that's probably absurdly large, but 200 kilograms. Is that really big? Okay, good. 200 kilograms. The reason we can understand. So, what makes it appropriate to describe it that way? The reason we can understand such properties, physical quantities, in this way, that they belong to families of properties which have a structure in common with the real numbers. Because the family of properties which are weights or masses, in my example, of physical objects has the structure, we can, given a unit fixed by a standard object, use a number to pick a particular one of the properties out of the family. So the suggestion here, which I've summarized as representationalism, is that quantities are properties which stand in higher order relations to each other. Now, what do I mean by a higher order relation? I don't know anything fancy about higher order logic. If that's something you're familiar with, that's not what's going on here. I just mean it's a relation that holds of properties, right? So maybe I'm standing. That's a property that I have. My hairline is currently above yours because this is where I am. That's a relation that we have as we're not properties, we're other things. But now consider the relation. This is instantiated more times than that. Well, properties are things that are instantiated, so that's a higher order relation in a relevant sense. Just a relation that holds between properties. So these higher order relations are relations that hold between properties. And I'm going to walk through really quickly sketch a particular variant of this that works for mass, for instance. You have to do different ones for different particular examples of properties, but I don't have to, but it's natural to. But one thing that you might say about mass properties, relations they can stand in with each other, is some are bigger than others. Not bigger properties, like this property and this property, but the things that have this property are heavier or more massive than the ones that have that property. It's just a kind of ordering relation on the masses. So we have the property A is, do it like that, is no larger a mass property than the mass property B. That's just one. And there's another one that's often used, which is generally called a concatenation. And the idea is just, it's the mass property you get by snapping those two together. So if you think, if I've got, I've got two weights sitting on a scale, perhaps. Two weights sitting on a scale, that has a mass property and that has a mass property. But the two of these combined has the concatenation of that. So you might write that. A and B are mass properties. There's another one, A concatenated with a B. And there's some very fairly intuitive, fairly straightforward sort of things you might want to say about these. And when you say those things, having said it, you can then put it like an axiomatic theory and then you can prove a theorem. It's a representation theorem. And I'm going to say it in a way that's a little different than how it's usually said, but a way I think is maybe intuitive for our purposes. What you can prove is there's a unique, what I would call ratio function. That is a gizmo that takes two mass properties and spits out a number. It's a unique one that has three following features. The first feature is that, intuitively, what you should think of this as doing is giving you the ratio between A and B. Right? What would be an example of this? Well, take the mass property of 100 kilograms, what we call that. You concatenate it with itself. That gives you another mass property, one we call 200 kilograms. There's a relation between those that intuitively the concatenation of that with itself is twice the first one. That's kind of the ratio. That's the intuitive idea this function is meant to capture. But the formal principles that it captures are if this gets assigned a smaller number than this, if and only if this holds. That is, holding fixed the denominator mass. Larger masses get bigger numbers. And that's the first one. The second one is that the concatenation of A and B relative to C is the same as the A relative to C plus the number you assign to A relative to C plus the one you assign B relative to C. So concatenation is working like addition, essentially. And the third one is just that every mass property relative to itself is 1. Because, right, ratios, everything is 1 of itself. So it's kind of this unique, and that thing's unique. And then you can think of units as follows, as Stalnaker says about a standard object. When I say like X kilograms, that just means, if I say if I'm 200 kilograms, that means take my mass property, put it in the top of this function, take 1 kilogram property, put it in the bottom of that function, the number 200 gets spit out. So this function then gives us sort of a way to use numbers to name all of these different properties, but the fundamental story didn't have anything numerical in it at all. It was just like this. It was just saying stuff about what concatenates with what and what orders with what. So that is representationalism, kind of a quick sketch of it. Have any clarificatory questions? I think this is a good time to just stop and take stock. I'm not seeing any, so I hope that the thumbs up, or is that a thumbs up? All right, all good. Excellent. So I think it's attractive. I'm not the only one. So this idea, it's not new to me at all. I mean, Hartry Fields endorses a version of it in Science Without Numbers. Brent Mundy endorses a version of this. Very recently, a really nice book by Joe Wolfe defends representationalism. A variant of this with more bells and whistles. So it's an attractive view. I think it's attractive, but it has a problem. And the problem it has is one that was, to my knowledge, first noted by Dave Baker. And it kind of goes like this. So consider the actual world. It's a good world to consider. Consider a time slice of the actual world, where a rocket has just blasted off to go into space. And the rocket is like just barely going to make it. It's exactly at the escape velocity. If it went any slower, it wasn't going to make it, but it made it. It's going to go out into space. And you pick a time slice, so it's reached that velocity, hasn't made it into space yet. And now, consider another possible world. Actually, the time slice of a possible world, call it Pandora, where it's exactly like the actual world at that time slice, except all of the masses are doubled. Everything else is the same, but the masses are all doubled. Now, here's one thought. Intuitively, this mass doubling should be kind of like a Leibniz shift, right? It's like you've moved the whole universe sideways, but there's kind of nowhere for it to go, so really you haven't described a different situation. Another way to put it that maybe is a little more careful than that intuitive gloss. I'm not going to go through the argument as it is on the handout, but you can look at that if you want a more careful formulation. But the idea is just, when you look at how all of the objects in one world are related to their mass properties and others like via these things, and how they are that way in the other world, it sort of carries over the same. Like, if my mass property is twice your mass property in the actual world, then my mass property is twice yours in Pandora. Of course, they've both gone up, but that's universal. So we can't find any way to distinguish me relationally to all the other mass properties out there. But the fundamental story, or so it seems, about how the mass properties do their thing is one that just involves these fundamental relations. Right? It doesn't say anything about A itself. It's just A is smaller than B. A is concatenated with B, or so on and so forth. So you could construct sort of a function from one world to the other, and it wouldn't preserve the mass properties, but it would preserve all the structural relations that are given by this here. And that, at least prima facie, seems like a really good reason to think that there's nothing going on in this world that is fundamentally different in a way that the laws of nature would sort of see or know about. The laws of nature, the idea would be they know about this and they know about this. There's nothing in the laws of nature that talk about particular mass properties. It talks about kind of the relations between them. That's the intuitive thought. We can go into more of that in the Q&A if we need to. And we also, sorry, I didn't mention this, we're supposed to suppose that the worlds have the same laws of nature. So if that's right, then it looks like since the actual rocket makes into space, Pandora's rocket makes into space. Right? Seems plausible. Other problem. We can actually write down the law of nature. It's on your handout, on page 2, of the velocity that the rocket needs to make it into space. On either planet, to calculate the velocity, you got to do a bit of math. And I won't actually do any math because I'm terrible at it, but I'll just write up the formula. So the velocity, is it just R? I think it's just R. Yeah, so W is for the world. So this is the velocity the rocket needs in each world, is the square root of the gravitational constant times the mass of that planet in that world divided by the radius of that planet in that world. That's the escape velocity formula. Now the thing is, when we plug this in for the rockets, one on Pandora, one on the actual world, this is the same, because we didn't change anything about velocities or distances or times. This is the same, but in Pandora, this is twice what it is in the actual world. So the velocity the Pandora rocket needs is the square root of 2 times more than the velocity that the Earth rocket needs. But we said the actual rocket only barely made it. If it had been any less, it wouldn't have made it. So we should think, oh, in Pandora, the rocket isn't going fast enough. It doesn't have enough velocity. It's going to crash. It's going to not make it into orbit. And now we've got a problem because we have 2 apparently good arguments for opposite conclusions. They can't, of course, both be right. And we need to diagnose it. What's gone wrong here? Now, I'm just going to, okay, so that's the problem that's setting up to solve. Now, this problem, or so I will boldly assert, is a symptom of another, maybe more deep problem. And that is, consider like the gravitational constant. It's approximately 6.67 times 10 to the negative 11, if Wikipedia is to be believed. Meters cubed divided by kilograms times seconds squared. That's all the denominator. Okay, I don't really care about the number, but notice there's that chunk of units. There's meters squared, and like there's your cube, the cube distances, and there's all this stuff about divided by masses and stuff like that. What is that? So the representationalist can tell us a story about what it is to talk about a meter. A meter is a particular property. We know what that is. Or at least representationalists, we know it if they're right, but we know what that is supposed to be. What is a cubed meter? Much less a cubed meter divided by a mass. The representationalist doesn't say anything about that. That wasn't part of the story. The story was just about the individual quantities, not these kind of more complex, what they call dimensioned units, where there's kind of lots of different dimensions doing all kind of math stuff with each other. Like we're not actually dividing properties. Properties aren't divisible in the relevant way. I mean, certainly on this metaphysics, a distance is not divisible by a mass. It's just not a thing this metaphysics kind of makes any sense of. But yet we've written down a law of nature that's got something like that in it, and we don't really know what it's representing. This metaphysics hasn't told us yet what it's representing. So I will boldly assert what we need to add to our metaphysics of quantities at this point as representationalists is a metaphysics of dimension quantities, and particularly the ones that show up as constants in the laws of nature. Now, I said I boldly assert that. The argument for that is not, I'm not going to try to draw for that directly. It's rather to be, say, look, we'll develop one of these metaphysics, and in the end, it will solve our original problem. And that's the argument that that's what the problem was hiding. So the task, and this is the task then for basically the rest of the talk, is going to be to try to develop a metaphysics of constants, or metaphysics of various things, some of which will be constants, that will serve our purposes. What do we need to do for that? We want three things. One thing we want is, since constants are the sort of things that we represent by numbers, given a choice of unit, we want to make sure that our theory predicts that whatever these things are, or whatever's doing the work of a constant, in the end, is going to get represented by a choice of unit. Ideally, this will happen automatically, just kind of fall out from the representation function that we already had for the individual constants. That would be ideal. I'm not saying it has to be that way, but it'd be nice to try to do that. The second thing is, however that goes, these also had better scale appropriately. However that, so like the idea here is if the gravitational constant is 6.67 times 10 to the negative 11 meters cubed per kilogram second squared, then we have a procedure for turning this into something with grams instead of kilograms, right? Which is, we put a kilogram up here and put 1,000 grams down here, blah, blah, blah. Anyway, we have to divide this by 1,000 to get what we want in meters cubed. It's grams times second squared. And so, however, the numbers are getting generated out of our metaphysics of constants, also better scale, right? Otherwise, things will have seemed to have gone kind of very badly. And the third one I put there, not because it's actually constraint on the metaphysics, but because it's the only way I'm going to justify my bold conjecture that I made, is that it should explain why the rocket crashes in Pandora. So that's the goal. That's the goal. All right, I'm going to stop again because now it's really kind of shifting from one gear into another, so it's a good time to check any questions. And yes?
Sorry, can you just say a tiny bit more about the second Isidro experiment?
Yes.
One by a tiny bit too far.
Sure. So the thought is just somehow or other, what we want to make sure is, maybe I'll put it in a different, I'll motivate the desideratum in a different way.
Thank you.
Well, here's what we really want. We want a metaphysics of constants where whatever the gravitational constant is, whenever we pick a set of units, this ends up getting assigned to a number, a unique number, but not just any number, the right number, the one that the scientists tell us is right. And depending on the set of units, right, if the set of units are the kind of meter and kilogram and second set of units, there'll be one particular number. If it's the meter and gram and seconds units, it'll be a different number that'll be divided by 1,000. And so if we're gonna meet that condition, then it had better be. That's what the scaling. That's what the second thing is sort of guaranteeing. It's not just there's some number, but it doesn't quite guarantee it's the right one but it guarantees that if one of them's right, they're all right.
Oh, thank you.
Let's talk about the rightness a little bit, if we need to. There's things to say about that I'm not planning on saying kind of in the talk. So but yes, that's how that's motivated. Okay. All right. So there really is a kind of issue here, and it's maybe not obvious quite how to see why there's an issue here. So I think one way to go through it is to walk through some kind of warm-up exercises. So we're going to imagine some fictional toy cases using completely made up and highly implausible physical theories, just to kind of see what the metaphysics would have to be, representationalist metaphysics for those physical theories, and what our options are. So, first toy theory are these things called additive Z fields. What's that? I don't know, I made it up. It's a kind of field scientists can make somehow. And the only thing you can ever get inside of these are a pair of iron spheres. Anything else was kind of bounce off, but two of those in there. And it's just fine unless the masses of the two spheres add up to 1 kilogram, in which case they just vanish. Okay. Kind of crazy and simple, but. So now we have a law of nature in this world. 2 iron spheres in a Z field vanish if and only if their masses add to 1 kilogram. And then if we're representationalists, we can wonder, like, what does this amount to? What is that constant? What does that 1 kilogram mean in this law of nature? But here, there's kind of a simple answer that presents itself. We have the property of 1 kilogram mass. Maybe the constant is just that thing, right? So it's when these two spheres have properties that concatenate to that thing, they vanish. And then the problem solved. So that looks kind of really good. The reason to bring up that example is precisely because it does not work as soon as you try to make it even a little bit more complicated. So now consider, instead of the regular old additive Z fields, the multiplicative Z fields, which I will now just call Z fields because multiplicative is too many syllables to say over and over again. So there's a Z field, and in a Z field, it's the same sort of deal. You get 2 spheres in one of these things, they eventually vanish. But this time they vanish when the product of their masses is 1 square kilogram. Law of nature, 2 iron spheres in a Z field will vanish if and only if their product, their masses is 1 kilogram or greater. What is that constant? What does it refer to? So let's start by trying the exact same thing. Oh, it refers to the property of 1 kilogram mass. Here's why that won't work. And it actually is directly because of this condition 2 that you asked about, that it won't work. But here's a way to kind of make this vivid. Imagine 2 scientists, Kit and Greg. Kit is working on this, trying to figure out the law of Z fields, what's going on with them, and he is working in kilograms. And after a whole lot of experiments, he figures out, suppose he does a lot of experiments. Let's use one as an example. These guys, where he's got a 2 gram mass sphere and 2 kilogram mass sphere and a half of a gram mass sphere. And since those, in fact, have a product of, 2 times a half is 1, so I'd be 1 square kilogram. Those guys, poof, they vanish. So Kit says, aha, the vanishing constant is 1 square kilogram. I mean, he has a bunch of stuff like this, but his best fit curve tells him this is how it's going to go. Now Graham is doing the exact same thing. Well, whenever Kit sees 2 kilograms sphere, Greg sees a 2,000 kilogram sphere. And whenever Kit sees, that should be a K, Kit sees a half kilogram sphere, Greg sees a 500 gram sphere. So what does he work out this to be? Well, again, if I did my math right, he works this out to be 1 million grams. That's what 2,000 times 5 is, right? Squared. If you want to calculate, want to check me on that. I was confident until I wrote it up. I was like, oh, Alex, wrong. I felt bad. Okay, excellent. 1 million grams. Now, the issue now is that take that one property that gets called 1 kilogram by the kilogram set of units. That property is not called 1 million grams by the gram set of units. It's called 1,000 grams. Right. So this property, if this property is actually the constant, then even if the law of nature stated in kilograms got things right, you stated in grams, it would get things wrong, and that would be bizarre. It's like, this is supposed to be like a notational change. So we can't just take that property of 1 kilogram mass, say that guy, that's the multiplicative vanishing constant. It doesn't scale right. Now, intuitively, the problem is, when you think about moving from here to here, you multiply both of these by 1,000. So you sort of multiply 1,000 twice. But when you move from the property of 1 kilogram to, you change that into the gram set of units, you just multiply that number by 1,000 once, not twice. So that's why things don't scale right. So now we can sit and think, okay, simply using that single property, that's not going to work. What else could we use? Well, here's a thought. We have, in addition to like a single property, we have sets of pairs of properties. Which ones? The ones where vanishing actually happens. So let's try maybe some blue for a bit, there's some properties, A and A, and then like B and C, and so on. It's an infinite set, where vanishing will happen exactly when, for something in here, one of the spheres instantiates one of them and the other instantiates the other. And if we use, say, the kilograms, this might look like 1 kilogram, 1 kilogram, and this might look like 2 kilograms, a half a kilogram. And if we were doing this instead in grams, this would be like 1,000 grams and 1,000 grams. This one would be like 2,000 grams, 500 grams, and so on. But the properties they're just sitting there. And it turns out that when you take just the properties and you apply this and use the number as the number that gets spit out when you kind of multiply any of these together, you're going to get that same, that single number that's unique that will change correctly as you switch from sets of units to sets of units. You're going to get what you want out of it. So the set of pairs of properties, that has the nice feature of meeting condition number 1 and condition number 2. If we identify that as the constant, the vanishing constant in this case. And if on top of that we said, and here's how you get the number that represents it, pick really any one of the pairs in there, and then in this case just multiply together the numbers that are assigned to each of the bits in it. So that's nice. It meets condition 1. It meets condition 2. Now, there is a sort of objection that you might have. And if you don't have this objection, like, more power to you. I'm not saying that I want you to have this objection necessarily, but it's not a crazy objection to have. It's a very natural thing to think. And it's like, sets of ordered pairs? Those things are like making things vanish? That's like, that like lives. Whoa, man. That's not going well.
They're magnetic. Yeah.
Oh, okay. Well, I don't know.
It goes right on the board.
On the board. Those are other magnets.
I see. Okay.
They're very confusing. I've done the same thing teaching.
Maybe you shouldn't have reeled that. I don't know. Anyway. So the objection that you might have, I'm not trying to say you should have it, but it's not crazy to have, is like, look, the sets, those are just things that sit up in whatever kind of platonic heaven that sets live in. they don't get involved in the laws of nature like that. They just kind of hang out there. Like, they shouldn't be part of the fundamental laws. They're in the wrong spot. They live over there, and the laws are happening here. There's various ways to kind of push these intuitions. I'm not unsympathetic to this, by the way, but if you are unsympathetic to it, then you can just kind of stop here and not have to worry about what I'm going to say next. But if you are sympathetic to that, there is a kind of natural response. I do think that there's more to be said in favor of moving to this kind of view, but I'm not going to say it all right now. And that is to think of, don't think of it as a set of ordered pairs that, things kind of abstract and whatever it's going on. Think of it as another higher order relation. And that set of ordered pairs, that's just what we call the extension of the relation, the sort of spelling out of everything that relation holds between. But really what's going on is just particular pairs of mass properties are related to each other in a certain way. The laws of nature say, oh, when that happens, make the spheres in a Z field vanish. So that's the kind of positive proposal about the Z fields. Okay. So that, I think, it's an attractive proposal. It's the idea of thinking about these as relations is not novel to me, although sort of this way of kind of getting there is. But what I'm going to say next is. The first thing to say is simply asserting that there is such a relation isn't actually enough to get us one or two on those constraints. I mean, the relation could be, who knows how the relation is? There's no reason to think just because there's a relation between mass properties, it's going to be something that for like any two things that hold, you'll be able to extract some number from them. Like here's a relation that can hold between two mass properties. It's a relation of I have one and you have the other. And it's not at all clear that there's going to be some one number that magically sort of comes out every time we take that relation and like apply it between the masses of any two people. Like that would be kind of weird. You wouldn't expect that. So we need to say a bit more kind of structurally that will guarantee that essentially when we put these masses, get numbers for the individual masses that are standing in this relation, they're going to math up in the right way. To put it another way, we have a relation, call it van for the vanishing relation. What we have to do is also say, in some sense, that this has the structure of a square mass. And what does that mean? Well, it means there is a number where for any A and B, van holds A and B if and only if, and here, let's see, this is going to be relativized to units. The number assigned to one times the number assigned to the other equals that fixed number. For example, like we have to say, look, there's whatever units you pick, when you take any two things that bear vanishing to each other, their numbers in that set of units are going to all multiply up to the very same thing. Otherwise, if it was like for these two, it multiplies to 7, but for these two, it multiplies to 9 for the very same set of units. That's not a constant. That's a variable. It changes, varies. It's got to be the same number each time. So we need a way to sort of say that. Now, I'm going to check the time. It's a little late. It turns out, happily, this can be done. The first thing to know is the stuff that let us cook up a ratio function, all of the background kind of stuff going on here, and this is, I will happily talk about this in Q&A, but I'm not going to go through it now because it would just be too much, I think. But that can be used to define a four-place relation, say on masses. I'll write it like this. A is to B as C is to D, that intuitively says the ratio of A to B is the same as the ratio of C to D. So if A is, the concatenation of B with itself, and C is the concatenation of D with itself, this is going to hold because they're both basically 2 intuitively, and it holds completely generally. Now, what we want to say is, and this is going to be sloppy and I shouldn't write this way, but I will, is that A times B equals C times D. Because the numbers assigned to A and B will equal numbers, where A and B are both kind of vanishing each other and C and D are both vanishing each other. Now we can't say that because we don't know how to times properties, but we can cross multiply. This is going to be the same as saying A, I want to show you this right. Okay, good. A divided by C is equal to D divided by B by just kind of cross multiplying. And this we can say using this kind of notation, right? I mean, I just reverse, it's A is to C as D is to B. So we can say that van is a square mass by saying that for any 4 things, if A and B van each other and C and D van each other, then this holds. Now, whenever this holds, these two will be assigned the same ratio by the ratio function, which means that this will hold in any set of units, which means this will hold in any set of units. And so we get the kind of result that we want. Stop. Seems like a good time to take questions. So there was a bit of math there. So either, there aren't any questions, or I've lost everybody hopelessly and I should give up now. Hopefully it's the first, but I will press on then. So there's 2 things that are left, and I don't have enough time to go through both of them this morning. One is that this works really nicely for when you just have a 2-place relation, but what about like a cubed mass? If you wanted to do the same trick with a cubed mass, you'd say, well, A times B times C equals D times E times F, and you do some cross dividing to get A times B divided by D times E equals F divided by C, and then you try to translate that into this kind of idiom, and it would be, well, what? It would be something is to something as F is to C. But like these guys are products, these aren't things that we have just, the best we could do with these are something that are like relations, like the relation that holds between any 2 things, if they kind of do this to A and B. But we don't know what it means to say that like a couple of relations are proportional to a couple of properties. That's not something that we're just given to work with in this kind of system.
Professor Turner,
Yes.
could I interrupt you?
Yes, please.
Because maybe others were confused.
Good.
I think that D over B has to be flipped. A over C equals D over B. I think it's A over C equals B over D.
No.
Oh, okay. Then I'm
So,
sorry.
but I'm glad you asked that because so A over C equals D over B, that will hold when the proportion between A and C is the same as the proportion between D and B.
Oh, okay. Right. Thanks.
Right? which is another important thing because you might have a constant that's like dividing and not timesing. So that is correct.
Okay. So, sorry to interrupt. That makes it.
It's
that
because
makes
of
sense.
because of the weird timesing thing that this works out the way that it does.
Sorry, I missed that part. Thank you.
Yeah, no, that's fine. I'm glad you brought it up because you're right. I mean, when I was writing this, I would stare at that and be like, that can't be right, and have to go back. So I totally take it. totally take it. Good, so we've got that. So here's the trick we can do here too, though, which is to know, A times B, pick any number you like. There's, say U, there's gonna be some number, say, I don't know, X, where X times U equals A times B, and Y times U equals D times E. So you kind of like use U as like a way of filtering out the fact that there's two of them, and then you can make this kind of expand more and more and more. I feel like given the time and given the level of detail, I'm going to leave it at that, and then we can ask more questions in Q&A if you want to go into this in more detail, but I feel like it's getting a little bit geeky at this point. The other thing, and this is I think a lot more important to worry about, is what exactly, so what's really doing, what turns out in this kind of way of thinking about the constants is what's really crucial at the heart of this metaphysical picture that's doing all the work is this kind of proportionality thing. These two properties are proportional to these two properties. And as long as we're just talking about masses, or just talking about all lengths, or all of that, everything's fine. But the gravitational constant had mass and length and time all mixed up in there. Like, does that even make sense when some of these are masses and some of these are lengths? So Dave Baker, who does endorse, I think, like a variant of this with all the bells and whistles that I'm kind of going on. I mean, he worries about this at one point with a really kind of quick quote where he says, it sounds like nonsense to say that a planet is twice as wide as it is massive. That's garbage. I don't know what that is. Is that what's going on if I say, as I will need to, mass 1 is to mass 2 as distance 1 is to distance 2? Isn't that the same kind of nonsense? That's the word. Now, why do I need this? Well, consider a different version of the vanishing. Now it's this one sphere that's going to vanish. It's got substance. It's going to vanish when the product of its mass to its diameter is a certain thing. Well, how's that going to go? It's going to have to be that mass 1 times diameter 1 equals mass 2 times diameter 2 for some, every time a mass and diameter in the right spot to make the sphere vanish. And when we grind through this kind of cross multiplication, the claim we need is exactly, is the reverse of this one. Mass 1 is to mass 2 as diameter 2 is to diameter 1. That's what we need. Isn't that nonsense? So the short and sort of interesting and important to spell out, because I think this hasn't been seen by people working in this area so much, is no, it's not nonsense. Because it doesn't say anything at all like something is twice as wide as it is massive. And so to consider an example, suppose I'm twice as massive as you. I don't know what it says about me and your diet, I don't know. Suppose that. Now, consider also this line. Right? This line, as I just kind of measured out, is twice as long as this bit of my hand from here to here. Those are just ratios. It's just counting. When I count how many hands I've got to copy over to make this line, it's the same as when I count how many U's I need to mass up to me. And that's perfectly sensible. There's nothing at all that's nonsense about that. You just understood what I said, right? So it works just fine. So what looked, I think, to many to be really deep and fundamental worry for even trying this kind of thing turns out to not be a problem at all because, this thing is not nonsense. And on top of that, and this is what really would take too far afield, but we can actually use the apparatus of this to define it, even when we have the kind of different mix. We don't have to say anything, we don't have to ever link a mass and a length here, or length and a mass and a length here, to be able to define this out of it. So we seem to be kind of on the right track. Okay, so how does this all play? Now, so now I've got, I think, a metaphysics of constants that meets at least our first two conditions. What is a constant? It's a relation. It's not just any kind of relation. It's a relation that can be represented by a number because, and here I don't have a good term, but there's either it's like a square or a cube or a ratio of squares to cubes or whatever of stuff that can be spelled out using this kind of ideology. And the laws of nature then kind of are responsive to what this relation is holding between. That's sort of the picture. So what does this say about Pandora? Because that was what got us here in the first place. We opened Pandora's box, we wanted to kind of get out of it. What is going on with Pandora? So the first thing that it says, well, we need to think about the laws of nature. This one turns out to be a little hard to think about in this context. So we can think about just Newton's kind of general law of gravitation. But that's even weird too, because that brings up a whole nother topic that I didn't want to go into at all, which is like, it's got forces in there, and forces are vector quantities. They've got a direction in space. And this metaphysics, I've said nothing about how to think about forces and so on. So I don't want to have to deal with that. So let's just use a really simplified version of Newton's gravitational law that holds when there's no forces acting on something. What is it going to do? So in that case, it says, it's an object doesn't experience any other forces, and there's a distance r from an object of mass m. It's going to accelerate in meters per second squared towards the other object, and that's going to be equal to g times the gravitational constant times m divided by r. Now, if you take the kind of current metaphysics of constants as being proposed, what that'll turn into is you have an object, that's experiencing no other forces and all that stuff. Then its acceleration, given in distances for any distance in time, this accelerates distance times that time squared, is going to bear the gravitational relation to that thing's mass and those two times. Sorry, what I have in the handout, there's a gravitational relation, that constant, to the radius with itself, and the diameter, and the mass, and then the time again with itself. That's just how that plays out, which is kind of a simple and elegant law of nature in terms of just, this is what's going to happen. And then we got to say, that G, I have to say something kind of complicated that I didn't write out to make sure that this is going to all end up under every assignment of units, kind of mathing up to a number that transforms in the right way. And that's the kind of picture. Now, this doesn't yet say what's going on with the rocket, but we are now in a position to say that. So essentially what you do is you start here and you solve for G. In the actual world, where the rocket makes it into space, what's going on is that you take the acceleration of the rocket in terms of a distance and a time, and you plug those into the gravitational relation, along with the Earth's mass concatenated with itself for various reasons, and the radius of the Earth. Like, that relation holds between those properties in the actual world. But when you jump over to Pandora and you look at what's going on there, you've got the same distances and the same radiuses in the same times, but different masses. And when you look at the stuff that's holding over there, the gravitational relation does not hold between those properties that are holding over there. So I said early on, like, look, in the actual world, if I'm twice your mass, then in Pandora, I'm also twice your mass. And that is absolutely true. What is not true is if in the actual world, you and I, plus these other things, grav each other, our properties stand the gravitational relation, then in Pandora, you and I and those other, the property I have and the property you have massive and those other ones grav each other. That's just false. So there's not really, these two worlds are not really the same in terms of all of the structural relations, the higher order relations that hold between the various quantities that they have. And that's why, according to this representational picture anyway, in Pandora, the rocket crashes. So that's all I have. Thank you.
Okay. Sorry, was there a question?
No.
Oh, okay. So thank you so much. And we're going to take our 3-minute break and reconvene for questions.
It's some amount of time, some quantity. It's between 3 and 7. Jim? That's
I'm so sorry. I'm gonna go back. I was just
That's fine. Yeah.
I got it, but like he was just.
No, that's fine. I've learned too much from sometimes I don't know. I've really caught it wrong.
Here's my favorite.
Like those suggestions to me are like old men.
This one makes it. When I start talking,
Easy for you to say.
when I start talking, and I say, oh my God, that's exactly the thing.
Yeah, well, we should.
Friendly college
Because the force on the rocket.
Gary, not knowing that they were recruiting Gary to, and he didn't just meet here the week before, gave a talk, and they were
Of course, it's also because of how you're supposed to do the math.
And then like 2 weeks later, I call him for coffee, and it's in that time we sit down, and
Well,
he's
talking
like,
about how strong and weak plot, you know,
okay, well,
the whole
it's
thing.
a new immediately, but I was gonna tell my own offers.
Stay in.
But there might be something.
You're big enough, it's all right.
But
Gosh, we're just gonna keep it secret.
that's the puzzle.
Well, it just seems like I don't know if we. This is the move, basically. I mean, all this could still be.
When I was fresh out of graduate school, I had at Ohio State. Shapiro was
The
there.
vanishing thing happens.
He just shakes his head and mutters.
Go down square. The guy who's doing that is just confused. He's already stated law.
And unfortunately, I was warned in advance. I knew, but I was like, if I had not known, I would have thought, wow.
Well, I got a little bit of like turn around.
What's the matter? Someone do something.
Philosophy. Kilograms by gram.
Yeah, it was very disconcerting. But some people just check sometimes to like see if something that might come up.
Oh, yeah, that's right. To get one. And he forgot to
Right. I've heard that. Yeah. So, but what was your point? So,
Well,
one
my
guy.
point is, look, if I give the law as the advantage when you get the property one square, then you want to convert that to squares. You don't do the property like that.
Yeah.
Because that's changing the law. That's changing the law. The law we've already stated, the conversion of grams is 1,000 grams squared.
But I thought that was something else.
At all.
It didn't seem to
I don't know if I like really overactive.
I thought the point was, kid
Because I was
does
at
his
Florida State. That's
independently.
Yeah, but one of that's right.
I was saying that from the hand.
And the law is one that's like, I'm saying two laws.
Realizing I was doing that is kind of disconcerting.
It should, when A and C, when the ratio of
Anyway, constant's just a proportionality.
that should definitely remove us. But I was very much more.
Gotta get the units right, that's why we have this stuff. But it's just
They all
conversion.
have the same general, right?
Right, and they all, yeah, it's all like mathematical.
Just by saying, but
Watch your age.
No, I
once you
totally
figure out
agree.
the mass interaction with all
It's really
opposites,
interesting.
all sorts of things.
I'm wondering about something related to that with regards to the
I feel a lot, I don't know, it seems like a lot hinges on what needs to be done.
but I'm wondering, is this genetic primarily, or is this really just a matter of by identifying with him and
Same law, same as the law.
It's hard to figure out this.
It's the same thing as getting
Laws
itched.
involving electrons.
Like the same, you can get the over again for the same reason.
Yes, we're only not see overprotection.
There's no electrons anymore?
So it's, what was throwing me off is I wasn't paying attention.
What you're saying electrons disappear?
That's a,
No, this is just, this is like
guarantees.
where, the whole story about the structure. It's all in quantum mechanics.
So I think actually we're talking
And the laws of govern those things called forces that are not gravitational.
Oh, there may be typos on the handout. I should just I am a typo machine. I
Atoms
apologize
anymore?
if I
Imagine.
typo that confused you.
You clarified the one that was bugging me.
Oh, was there a typo on the handout? Typo on the handout?
Yeah.
I've never related to something more in my life.
Assignment assets to the subject.
Okay, so we're going to go ahead and get started. I am going to try to use the method that I gather I'm supposed to use, which is keeping a queue rather than just calling on people, having everybody raise their hands. I actually find that a harder way to do things, so it's not the way my brain works, but I will try my best. If everybody who has a question could raise their hands, I would be grateful, and I'll try to make a queue. And keep your hands up, and we're going to start with a question from Doug.
So,
Keep your hands up, please.
thank you very much for the talk, Professor Turner. I have a couple of questions. Let me just go for the first one that occurred to me, and it's way back in 2.1 for argument 1. Maybe this will just be a good time for us to talk a little more about more general motivations for representationalism, and because I was immediately a little puzzled by premise 2 in that argument. And I thought, wait, there seems to be, at least for certain sorts of metaphysicians, there seems to be good reason just to deny 2 straightforwardly, right? And thereby cast doubt upon whether or not representationalism about the laws of nature is giving us the picture of gnomic space that we want. I was just thinking of something like the following. Well, should we think that 2 worlds are going to have the same laws of nature, they don't differ in any way with respect to the natural laws, if there's this function from the actual world to that other world that preserves the representational structural relations? I immediately thought, well, wait, if you think, as I know many Lewisians do, I'm not going to take up a lot of time by getting into the complicated reasons, but you're probably aware of them, I'm not sure if others are. But there's Lewisians and others sometimes doubt that there could be sort of an unlimited space-time. In other words, that space-time there have to be in principle limits on the size of space-time. But I was thinking, if you think there's in principle limits on the size of space-time, so you're immediately going to think, well, there's in principle limits on the amount of mass that some possible world can have, right? So you might, right away I found myself thinking, well, if you buy that kind of picture, then maybe that provides motivation for thinking that the laws of nature for any possible world have got to say, they can't somehow be silent on this, they've got to say something about what the maximum amount of mass is, or the maximum amount of space-time taken up by stuff is. And if you think that's the case, then that would seem to provide motivation for thinking that somehow this preservation of structural relations can't be all there is to a preservation of the laws of nature, because there's more to, the laws of nature have to talk about more than just these structural relations, right? So I'm wondering if, so anyway, I was thinking, well, if you have this picture of what modality amounts to, and what the space of possibilities amounts to, then maybe that provides reason for denying two straight away. Anyway, what do you think?
Oh, good. No, thank you. That's really helpful. It's a little part because I realize one of the things going on is I think that that two's being interpreted in a way that I didn't intend.
Okay.
And this told me I did not do a good job of being clear about this. So when and it's because my definition of nomic twins is not as helpful as it could be. So when I said a different anyway relevant to the natural laws, what was not intended was the different anyway that's relevant to what the natural laws are, but rather to how the evolution will occur. So let me try a different way of approaching what the idea was meant to be. Because I did the point. I'm not sure that I'm not sure a limitation on space-time is a limitation on mass, because like what if you just have like a series of worlds with larger and larger, each of them have two things in them, one with like 1 kilogram and one has X kilograms, and X keeps getting larger and larger from world to world.
Yeah.
I don't want to fuss about that.
Right, but just like I was just thinking like there's certain.
There might be laws of nature that are not settled by this.
Yeah, or do you think there's like in-principle limitations on the cardinality of the set of individuals, or the neurological individuals to be in a world? Maybe that would get you.
But really, what I was thinking was a little bit different. It was thinking start with the idea of if I'm a Lewisian, it would be like a natural property preserving isomorphism. And Lewis, for sure, is like, if isomorphism preserves natural properties, then they have the same laws of nature, but plus they're going to evolve in the same way from any moment, given, or better if it's from time slices, given that they have the same laws and there's this mapping, they're going to evolve in the same ways. Setting aside indeterminism that might make them split later. Mm-hmm. So what I was thinking is, you start with that idea, but it's not exactly the case that between Earth and Pandora you've got an isomorphism, because, like, if you're thinking about some of the natural properties of the masses, suppose like the actual mass of the rocket is Maddie column, and then the mass of the rocket in Pandora is called Tammy, let's say, and we're like, well, this function just takes from Massey to Tammy, and those are different, so that's not really the natural property preserving isomorphism that you wanted. I mean, you're going through the rocket, but the thought was meant to be is, okay, but does merely noting the kind of quiddatistic difference between Maddie and Tammy give us any way to explain why this world would evolve differently than this one? Given that, and this is, I've said this in versions that people have objected to, but I'm going to say it now, and then we can fight about it afterwards. We have to. Given that it seems like the laws don't mention Maddie or Tammy, those particular properties don't seem to be what it's talking about. And on the representationalist kind of overall picture, what's sort of doing the work is not, well, the first thought, the first pass, what's doing the work is not the intrinsic nature of Maddie or Tammy, but the relations that hold between Maddie and the other things here and Tammy and the other things here. And given that that's what's doing the work in the laws, then it's sort of puzzling why the mere fact that this barely fails to be an isomorphism that way would result in different behaviors.
This is thank you. That's very illuminating.
Okay.
I'm tempted till I ask Paul, but I know if there's a lot of
I think there's a chance out to reach out to.
Yes, sir. Thank you for that.
Yeah, awesome.
Val?
Just a clarificatory question.
Yeah.
I didn't quite get the last move. So, can you explain how theory would deal with the example, not in Pandora world, but in our world, where we take some planet that is really far away from everything, and there is a rock on another planet, and the planet is twice the mass, the rock is twice the mass, and the rock is trying to take
Right.
the planet.
It would say the same thing. I can walk through it if you want a second time, but it wasn't, so, moving to a different world is what made bigger problems because if it's in the same world, the relationalist can say, but look, I can explain its difference because there's different relations being held between the rocket a billion miles away and the rocket here, where putting it in a different world, you sort of lose that comparison. But the idea, it would be the same story. It's that when you look at the time, the distance, the radius, the mass, and I guess this was just those four, whatever I'm missing. In the successful case, they all bear that G relation. And when you look at it in the unsuccessful case, they don't bear that G relation.
Joshua, are there any questions on Zoom?
There are no chat questions. If someone on Zoom does have a question, just type it in the chat. But for now, no.
Okay. Okay, Kirk.
Thanks for the talk. So, I don't know which question to ask, but
I can put you at the end of the queue.
no.
I mean, you can do now, and you
I
can...
will make a decision.
Okay.
Yeah. So I was thinking naively, there's not a puzzle to begin with because, of course, mass figures and laws that involve lots of other quantities, and even if you're just thinking about Newtonian. I was thinking, first of all, how are we supposed to think about doubling the mass of everything? We go down to elementary particles, and then
That's how the example's supposed to
all
work.
that stuff. I mean, it'd be a mess once you integrated with all the other laws we've got and all the other forces. So we wouldn't expect anything to look the same. But, leaving that aside, just imagine we're not going to go down into the details and think about quantum mechanics and the strong and weak force and electrodynamics and so on, right? We figure you keep everything else the same and just double the mass of everything. All sorts of bizarre things are going to start to happen right off. But just thinking about force laws, right? You double the mass and you double the force. And it's going to require much more accelerant. So if the rockets have the same amount of fuel but double the mass, then of course they're not going to make it. So you think I've solved the problem. Why didn't it even look like there's a problem to begin with?
I guess, right. So I hear that and I think that's not a solution, that's a statement of the problem. The problem is we have all this empirical evidence that you couldn't just double the masses and expect everything to not go wonky. But
we have an explanation, which is, mass figures and lots of other laws. You're not doing any changes there.
So I'm trying to think of how to. I guess the worry was meant to go this. The worry is meant to really stem from this thought. Like we've got a almost isomorphism between these two possible time slices of worlds. As an almost isomorphism, it does change what the masses are. They're all doubled. But it doesn't change what, according to this metaphysical picture, are the important facts about masses, which is how they're all related to each other. So given that...
Other physical quantities as well.
What's that?
They're related to other physical quantities as well, and that's what's left out when you just think about that.
Well, that's the conclusion of the paper, is they're related to physical quantities as well. But in what way?
Well, flat-footed, we write out the laws, right? And then we start deducing what would happen if you doubled the mass. Why do we need a lot of metaphysics to explain it?
Oh, I wasn't thinking we needed metaphysics to explain what's going to happen when we double the masses. Physics explains what happens, or tells us what's going to happen when we double the masses. What I was thinking is there was an independently attractive metaphysical view of quantities. But this metaphysical view of quantities leaves it very unclear what is going on, why it is the case that the physics acts the way that you do, that you suggest. And this, you said the reason, but the reason that this happens is because we have these constants. These constants act as coupling between, and we don't have a metaphysics of that. Until we have metaphysics of that, we don't have a story about why on this metaphysics of quantities, like why this metaphysics of quantities is consistent with what science tells us.
I feel like I should stop talking. And we should pick this up later.
I think you're looking at argument one, right? And you're thinking, but argument one says.
Yeah, argument one. And I think I'm looking at premise two. I mean, there's some question about how to interpret the first thing there. So if we're just thinking about the story about mass, for instance, to me, even just thinking of nomic twins as evolving in the same way, two is false. Doesn't even look like it should be true.
Great, and then I think, yeah, so I think that's fine, but then I think that the next move is to say to the representationalist, but why? What is your view? Hey, representationalist, it's a challenge for you. What is your view on mass that explains why, even when you preserve all the stuff that you said was important, like that's not enough to preserve what's going to happen?
Because that's not... The story about mass is, you can think about, if you go back to these old theories about the meaning of theoretical terms, right? They're given by the laws in which they appear, right?
Sure.
So there's more than just these relations that go into determining what the concept of mass comes to, right? So it's as if you say, so we have these ways of measuring, which is what this comes down to for assigning or ordering masses and so on, and their concatenations. And as if they say, and that's all we mean by mass. But it's not, because those aren't the only laws that are involved in articulating what the concept of mass is.
I'll just put it a slightly different way, and we'll leave it there. There's another way of approaching this, which I think is maybe speaks more to your way of thinking. I mean, this is probably presented dialectically because argument one is what Dave Baker's argument looks like, right? So that's where I'm kind of getting that from. But but other way of saying is, okay, like you've given me masses and you explained the use of numbers there, but you haven't explained the use of numbers in the laws, because the laws use numbers and constants in ways that are not settled by the use. So just say more about that, and then I'm trying to say more about that.
Fair enough.
Okay, so.
Alex? Yeah, this is kind of, I suppose, a follow-up, a bit less of a sophisticated follow-up, but I just want to make sure I understand the dialectic of the argument. You've got this argument one. I'm just looking at argument one. We're saying, okay, there's got to be something wrong here. One of these premises has got to be false. If I'm following, you're targeting the first ultimately? Is that right? The first?
I am targeting the first. I would be happy to target the second, because we can fight a little bit about what the exact extension of the representational structural relations amounts to.
Right.
If we mean just narrowly those things, then it's premise two I would reject. If we mean the higher order relations that the structuralists ought to believe in for their overall metaphysics, then I would reject one.
Okay, great. Yeah. And let me just put this real simple question to you. Why not look at three? I mean, why is it, I guess what I'm struggling, and maybe this comes down to how you're defining nomic twins, because at first I thought it was the laws remain the same, and the constants remain the same, and we're just, we're from moving our action from the actual world to the Pandora world, we're doubling the masses. And if that's the case, I guess I'm failing to see why we should expect it to be the case that the nomic twins will agree about whether the rocket makes it into orbit. Because the masses are doubled, you'll need more,
So three was meant to be sort of, almost analytic to nomic twins, right? So if you're thinking, look, of course that premise is false because when you double the mass, it's not going to make it into orbit. then I think it is premise 1 or 2, as I was intending the argument. I mean, I basically just introduced the term gnomic twins because I didn't want to have to write out if one, then a very long thing, and it was just abbreviation to, because my premises were getting really long.
Okay.
Was the intention there. So it's not meant as something kind of super deep.
Yeah.
What's really doing the work is one, and then like essentially if one, then the two worlds will agree, and I'm trying to gesture it at this kind of motivation. Look, I'm not unsympathetic to what either of you were saying. As I was trying to write in the handout, I was like, this doesn't quite seem as compelling as I'm trying to write it out. But the dialect, so here, there's a little bit of historical background. So it starts out with a paper by Shamik Dasgupta in which he argues for what he calls comparativism, which is kind of a variant of this. But really, like, he is motivated by thinking that a mass doubling is like a Leibniz shift. Like that's like, did I say the thesis of comparison, as Dasgupta puts it, is you double the masses and it doesn't make a difference. So, like, if you just automatically think that's like wrong, then you sort of know, it sort of seems weird. But that's not kind of the reaction that happened. And Baker basically, in making this point, does it by this rocket example. And so I'm sort of picking up from there. But part of the dialectic is and maybe this will be helpful. Part of the dialectic is just diagnose what goes wrong with, what Dasgupta is wrong about. Say which premise is false, that kind of thing. Another kind of project is more constructive, which is like actually build out take your metaphysics of properties and expand, or of quantities, and kind of expand it a little bit more broadly, so that it actually has that as a prediction and isn't merely kind of consistent with it. And so I think of what I'm doing is sort of more in that second line.
Okay. That's all.
Yeah. So it's sort of like, yeah.
Thank you.
Tim? Oh, Tim, I thought you had said you had a
No, I was
question.
just referring to Dave,
Oh.
because Dave's hand wasn't up very high, so I thought.
Okay. Thank you. Well, Dave, go ahead.
Hi, well, thanks for a fun talk here. I guess I had a question about vectors. You mentioned vectors
Yeah.
and quantities in direction, and I mean, I guess I take the end result here is we have constants, and constants are a number times some amount of products and quotients and stuff, and if you can account for those,
There's other relations, yeah.
then we're done here. Then I was like, okay, a vector is a quantity in a direction or something,
Yeah.
and how do you account for that?
That's an excellent question, and it's, so I said this is like just part of a much broader project, and that's one of the important kind of questions to work on. So I'll tell you, I'll just make a few gestures. There's nothing I absolutely love for a metaphysics of vectors. It seems to me, and then back up. And there's also something else that matters a whole lot, which is, are we doing this in a flat space-time, or are we doing this in something that's more suitable to general relativity? If it's the second thing, then that's another talk. Like, I need to, first I need to tell you what a differential manifold is and what that is without numbers, and and that's not obvious. But so let's go for the first one. Sorry, that's the empty. So in that case, I have a couple of thoughts. One thought is I am sort of attracted to the view that fundamentally there aren't any vectors. So all vectors end up being sort of emerging out of laws that are involving scalars plus evolutions, and thinking of those like step one, which is gonna lose me some friends maybe, but think of laws of nature as constraints on how you fill out a space-time. Step two, formulate them in such a way that the constraints are based on distribution of scalars plus kind of all the positions. And then all the vector talk ends up being stuff that comes out naturally by just kind of looking at chunks of space-time and the way that scalar quantities vary across it, like directions chunks. Again, like that's not to everybody's taste. No one likes that kind of thing. Another kind of view that is kind of close to that, but thinks of sort of vectors as kind of combinations of a quantity and a direction, like a ray that goes on kind of forever. There are things that are a little bit ugly about that, like when you try to add, you have to kind of do a little translate into the spatial and then translate out. Actually, sorry, yeah, something I wanted to say first. When we're talking in physics about vector quantities, actually one of two different things we might mean. So one thing you might mean actually is just quantity that, however it works, obeys the axioms of a vector space. So one kind of example of this is just even if your quantity is like something that you represent with complex numbers, then it's going to have that. And like those are, I don't worry about those. Those are not a problem at all. Like that, it's the sorts of vectors that we mean as we mean, it's like a quantity that points. Those are the ones where I think it sort of is tricky. Now, so yeah, the short answer is I don't have anything I really love on it. There's another issue that I have been thinking about related to this, and this is sort of defensive of sort of why I do kind of feel like we're going to have to move to this view where the laws, I mean, maybe they aren't, but they at least generate kind of constraints on how to fill space-time. Is very often we want to think of the laws as like, well, you take what's going on now and tell me what happens next. And I think there's a straightforward problem, which is there's no next. Right? Between now and any future moments, there's like a continuum of moments that intervene. And I think actually this ends up being fairly deep, but I haven't argued for that here, and I'm kind of not going to. But I kind of feel like the problems that we have, is also an argument for, but the problems we have thinking about kind of vectors in a helpful way ties in with that. Like, if I knew how to say, if there's thus and so force going on in this direction at this instant, then in the next instant, blah, 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 I feel like I could see a way to kind of give a metaphysics of vectors using that. But without that, I sort of start getting lost. So maybe that was too programmatic to be very helpful. But yeah, it's something I've thought about a fair bit. I actually think that it looks better in general with a differential manifold because you're going to have to get a different kind of vector structure. Sort of much long before quantities show up, and you can use kind of that. But sorry, I hope that wasn't too much insider baseball. That was just some thoughts.
Matthew?
Oh, thank you for a great talk. Yeah. So I had a clarificatory question, and then maybe we'll lead into slightly deeper questions. I want to just make sure I get this right. I mean, it seems the talk seems very complicated in some sense, but I wondered if the central kind of dialectical move was quite simple in the following sense, that is it kind of fair to say why the argument one goes wrong? Is it just kind of overlooks gravity? And then if that's right, I just wondered if you could say a little bit more about the kind of status of gravity and how it relates to mass. So there are lots of things you could say. I guess I was just wondering, is gravity a law of nature? And is there a kind of essential connection between mass and gravity? Or can we think of possible or impossible worlds in which kind of connection is severed between them? I think I need to know a little bit more about the metaphysics to see the whole argument.
That's fair. I think what I want. This is, I'm in sort of an awkward position to say what I'm about to say, but I just don't know how else to say it. Is that sort of actual proponents of stuff like this, representationalism, and they have looked at Baker's arguments, and it's not that they overlook gravity. They're like they also say, no, the problem here is what on earth is that gravitational constant doing? How should I understand that metaphysically? And I'm talking like, like Ted Sider and Hartree Fields, like have been, and they just have had to really struggle to kind of come up with something to say that they're happy with.
Right.
I mean, I know Sider says something in his most recent book that I think is his, well, this is the view I'm going to take, and I'm kind of forced to it, but I don't love it. It's not that, it's different than this. So there's a kind of, the dialectical situation is a little bit awkward just in terms of, so now when people are like, that argument looks terrible, and I'm thinking like, and I see what's coming from. I have a hard time kind of communicating maybe the slight difference of perspective between them. So what's going on in the literature, some people are kind of overlooking gravity. It's that they're feeling puzzled about how they should work gravity in their overall metaphysical picture. But now there's something else that you also asked that I think is very important. I've really kind of been silent about this, but I'm happy to. I don't know how long the queue is.
Just a few more people.
I feel like time seems pretty plentiful, if I'm not mistaken. So I'll go ahead and go to this too. So you asked a question about like, can it change?
Yeah.
So in her recent book, so Jo Wolf argues for representationalism, and I think she actually clarifies a bunch of stuff in the literature was not as well clarified beforehand. But one of the things, so Shamik Dasgupta has this view he calls comparativism that I mentioned, and he's just got like Leibniz on relationalism, but just make that for properties instead of for chunks of space. Like that's his kind of paradigm. And he calls it comparativism. And one thing, and then the discussion kind of got a little bit muddled. And one thing that Wolf does that I think is really nice is say, hey, we can make a kind of two different distinctions. And let's just go ahead and use the old-fashioned language for one of the distinctions, but this is about quantities. We have substantivalism on the one hand, and we have relationalism on the other. And the idea is just, this is part of what I didn't talk about in the relationalist version, but are there mass properties, or is it just that like, I'm more massive than you and that's where it ends? That's kind of one distinction. I'm bringing it up mostly just because it's not going to occupy it. So we're just going to stay on the substantivalist. There's all sorts of weird things that go on here. So, but the reason I bring it up is because it was in some sense not distinguished from this, which she uses comparativism versus absolutism. And I'm sort of saying to warn you, other authors before would use these as sort of equivalent to these, and I'm not doing that, and Wolf's not doing that, and so on. And what's important here is the idea is that the absolutist maybe believes in these relations, say, but the absolutist thinks that whether or not those relations hold depends on like the intrinsic nature of the relata. So what are these mass properties like? It's because of what this one is like and because of what this one is like. That, that holds, or that one, these two, this is the canonization of these two, or something like that. Whereas on this taxonomy, the comparativist says, no, they're external relations. The properties themselves might as well be just unstructured BBs. The relations are just kind of thrown on there. Now I bring all that up because once you have, we have these kind of structural relations, but we also have these constants you might think of like nomic relations. So like a gravitational relation that holds between a bunch of quantities on this view. And you can mix and match. Some things would be weird to mix and match, but in principle, logically consistent. But you could, for instance, be an absolutist about the structural relations. But comparativism sounds weird now, but in essence, a comparativist about grav. So whether or not gravitation holds between isn't a matter of like what those things are like in and of themselves, and that would be a view in which would be very natural to think that the gravitational constant could have been different. It could have just held among different ones of those. Whereas if you had kind of an absolutist view about grav, you would think, no, it's kind of much more kind of essential to the way everything is kind of playing together. So, I think certain early forms of causal structuralism where sort of all of a property's causal profile is like deeply essential to it. You would think they would probably like something like, reverse order of explanation, but there's a sense in which absolutism would be kind of attractive insofar as it's like sort of constitutive of like my mass and that mass and these times and stuff that we all grab each other, which really fits well. Personally, that's not the kind of view that I'm most attracted to, but I think all of this is consistent with a number of different ways of thinking about those issues.
I think that's really helpful.
Antonio?
Yeah, thank you for your talk. I was just a question about why you said at the beginning that the representationalism was attractive.
Mm-hmm.
So to see which could be like a motivation for it, because in your answer here, you mentioned that maybe one of the major motivations is to explain what actually are these numbers that appear in quantities. So, and you end up at the end of the talk with this Newton without numbers, and I was imagining maybe a motivation of why you find attractive representationalism because you don't want to have numbers.
Mm-hmm.
So right. I was just trying to figure it out with this that you attracted to.
No, thank you. And I'm a little tired. I skipped an entire 2 paragraphs where I was going to go through at the beginning, and I just jumped right past it. I apologize. I will do that now. So this is not my motivation. As I've said to others, I am interested in. So Harvey Field wrote a book called Science Without Numbers. He was interested in there being no numbers. So what he really wanted was reality without numbers. And getting him out of science was just part of that job. I'm interested in science without numbers, but I'm not really that concerned about reality without numbers. And there's a couple of different reasons you might like that view. One is one that Field also pointed to. It's just sort of the thought that if I smack the bottle and it falls on the floor, that transaction, the bottle didn't have to consult the kind of realm of Platonic things before it knew what to do. It's kind of all just right here. Intuitively speaking, so Field calls that a kind of intrinsicality motivation. That's for kind of a broad picture. When it comes to representationalism, narrowly, one thing that often motivates it, there's a couple of things that motivate it. One is, is just thinking that we need some sort of story about why numbers show up in quantities all the time. And that the kind of most flat-footed one isn't very attractive. So the most flat-footed one would just be, I'm X kilograms of mass. Sorry. I'm X kilograms in mass. That just means I bear a fundamental relation between me and X, which X is a number. Now, at a first pass, it sounds pretty good, but then you're like, wait a minute, there are lots of different units. So suppose I bear a fundamental relation between me and X, and that's the grams and kilogram, the mass and kilograms relation. I also bear a number between me and 1,000 times that, which is my mass in grams. What about that relation? Is it also fundamental? Also part of the universe as basic structure? And it looks like both answers are kind of unattractive. So if you say no, it seems weirdly arbitrary. It's as though there's like a privileged set of units. I mean, maybe it wouldn't be kilograms, but whatever the one fundamental mass relation that relates me to some number, like whatever it relates to one, that thing is like the privileged unit mass. And it's weirdly arbitrary that there'd be a privileged unit like that. The alternative is like, well, no, it's kind of all of them. You start thinking about all of the many possible units, like any real number, like you could find some unit that kind of makes that thing go. And then that just seems like bizarrely profligate. It seems super, what's the word I'm looking for? Not overdetermined, but it's like that. Anyway, it's too much, right? It's like when God made the universe, step one, decide what bears the mass in kilograms relation. Oh, we're not done yet. You've got to do that continuum many more times now. It feels like that's also a kind of uncomfortable view. And so that dilemma, I mean, means we should look for something else. And on top of that, just a lot, when you talk to people who don't worry about metaphysics a lot, about like, oh, I'm worried about like numbers and science, like, oh, come on, it's all just representation anyway. Like it just kind of this thing that often comes up. So there's kind of, I think, a confluence of several things. There's sort of an argument against the flat-footed explanation for something that needs explanation. I haven't argued this is the best explanation. I think it is, but I haven't argued for that, and I'm not really in a position to do that right now. But on top of that, there's a lot of people just find it kind of sort of intuitively right that numbers in science are mainly doing some sort of a representational role. And then tied to that, and very closely aligned, is this kind of Fieldian thought about the intrinsicality of the various causal transactions, like not sort of needing to be mediated by some realm of Platonic objects.
Good year.
Yeah, thanks so much for your talk. So I have a straightforward question about kind of how to understand how the basic building blocks the view together. So on the first page, we get a quantity is a sort of property we measure in units. So it sounds like quantities are properties of the same kind.
Yes, that's right.
And then when we get to the stuff about the vanishing constant, it sounds like, well, a vanishing constant is a fundamental high order relation between masses. So it sounds like a constant is a relation that obtains between quantities.
Yes.
So does that imply that constants are not going to be quantities on this picture?
Yeah, the way I've terminologically spelled it out, that is correct. Yeah, I mean, I think that's a bit of terminology. And what I was trying to do was more just characterize. So I say quantity, you want to know what is he talking about? Well, here's a kind of characterization. I'm trying to think whether these would be quantities. So Wolff gives an actual characterization on quantities are like this, and it's very abstract. And it might be that these things end up being quantities on that view, but it doesn't say that they're properties. I'm not super committed to that. It was rather, like, the picture is the kind of basic entry points to this discussion. Those kind of quantities, those are properties. Whether some of the other stuff we cook up, we want to call them quantities or not, is not something that I kind of want to get too involved in. There is a sense in which, though, like the adjacent quantities are, I don't want to say more fundamental, but they're more ground level in a way than the relations, because like the relations are just there to do stuff with them in a way.
It just seems like it'd be nice if the constants turned out to be quantities, because then we make sense of why it makes sense to represent them numerically.
We can make sense of why it makes sense to represent them numerically here as well. It makes sense to represent them numerically because basically the idea is, suppose we take a relation that is a mass product. So a consequence of that, since it's a mass product, is, let's see, for any A, B, C, and D, if those both hold, then A is to C as D is to B. So that's like step number one. Step number two, now we just apply the representation theorem, which tells us for any basic set of units, we're going to have any choice of unit we pick. I'll use F for the function that takes us from a property to its number. F of A divided by F of C equals F of D divided by F of B, and then we cross multiply, and this is going to be just some number, and we've just shown that any pair on any set of units, like for every set of units, F, there's some number that every pair is going to times up to. And so we sort of get that kind of falling out for free. And one of the things, so I think this is, there is another kind of suggestion people have gone for, which is like closer in spirit to me. What you're suggesting is you start out with, you've got like, here are the mass properties, they've got some structure. Here are the length properties. Let's introduce some mass lengths. Here they are, they've got some structure, and they kind of zap them. One thought about that is just that if you had to do it, you could do it, but it is sort of what this sort of suggests is it's doing work that we could have done without it. We could have kind of got all that for free. So that's just a sort of Occam's razor type argument. Another thing that people do worry about is there was that, does it make sense to say that the Earth is twice the mass of its diameter or something? There's a worry that if you do too much of that, that starts being the sort of thing that ought to make sense, and you kind of don't want it to make sense. So that's the other kind of motivation for this maybe metaphysically thinner way of approaching things. But that other option is out there, and I take that point. Sure.
Gary? Yeah, so thank you. I enjoy thinking about these problems, but I am puzzled. So let me start with something that I think Kirk was saying. I was puzzled from the beginning by the setup, because this is just a remark, and it'll explain where I'd like to go. What you start off by doing is talking about how you think about mass alone, just as a thing on its own. So there's a kind of atomistic story. Well, there's mass. Let's see how the masses are related to each other, as if there were no laws of nature or anything, just what they are through these proportions. And we've got mathematical relations between them, and we can assign numbers on that basis. And then, of course, problem, there's relations between mass and other quantities, and they're expressed in our physics with constants. Great. So solution, roughly, is what I would call a holism about representation. You have to look at all of the laws that we accept and figure out how you're going to assign numbers systematically to the various quantities of those different sorts in a way that makes those laws true. And to do that, I will grant you need higher order, essentially, proportions, like your, what you call it, square masses. Let's say that's all right, if I'm tracking. I guess what I'm wondering, and this is, I think, partly a version of some of the earlier questions, is what's left of the metaphysics here? I mean, it seems like, yes, you can do that, and actually mathematically you can talk about what those higher order products are. In fact, it's only mathematically that you can really do it. Then, so this is where my question comes. Given that we're doing this super complex thing with these theories that are incredibly sophisticated, we're going to get these very sophisticated higher order relations between quantities. In what sense are we getting to anything more fundamental than the math itself? We could say, oh, I kind of, sort of get that. But we don't really, in the way we get, okay, this ball is half the size of this ball, I see it right in front of me. You don't get that when you're thinking about gravitational constant or any of these very sophisticated higher order relations. This is not quite the question of does it make sense, because I'm going to say, okay, it makes sense. But it's the question, in what way are we getting into anything really deeper into the story in this by this route, rather than just re-expressing it in terms of these higher order essentially mathematical relations?
So, what things going on there? The first one is, I don't think I agree that these are mathematical relations. These are physical relations between physical quantities. Grav is a physical
ratios.
relation.
What are ratios?
Oh, I haven't defined what this is yet. And so maybe that's what the worry is. But
yeah, tell me, define that without it looking like a mathematical relation in some way which is intuitive and
why does that
more
be
basic.
why does that be intuitive? Like,
okay, whatever it needs to be for you to make progress.
So the first thing is it depends a little bit on what resources you're going to spot me.
Anything you want.
Without saying, oh, that's mathematics. So can I have a just as many as quantifier? There are just as many F's as G's. Is that okay?
No, that's math. That's a fundamental mathematical relation.
I mean, the reason I'm asking is there are 3 F's mathematical on your account?
Well, I mean, on the standard understanding, yes.
So there's an X and there's a Y and there's a Z, and X is distinct from Y and Y is X is distinct from Z. Like, that's mathematical.
Yeah.
If you think that's mathematical, then no, I can't do that. But I'm thinking being able to do that is very, very weak compared to thinking, I'm just going to help myself to like all of analysis. Right? I'm thinking like the people who are worried about mathematics generally think that, look, sort of quantification in adverbial position is fine. There are 7 F's. Is okay. So I'm just a little bit, you're challenging me to do something. I need to know what the rules are.
No, well, I don't know what your rules are. So is it this? Is it really, see, this wasn't clear to me from the talk. Okay. Is it that you want to really do all of physics without quantifying over numbers, but you're willing to quantify over, objects and things, but not numbers? So it's all about whether you need to have as values of your variables numbers. Is that it?
Let's say yes.
Well, I'm asking.
I mean,
I'm not arguing this. I'm wondering what it is.
So that would be a sufficient condition, yeah.
Because that was not clear from. So then you want to say I can characterize all of the kinds of relations and products and ratios I need to characterize the gravitational constant without numbers.
Yeah.
Okay, so here's another thought that occurred to me. Hartree Field, his story is, well, I'm first going to give you a way of characterizing all of mathematics without numbers. Now, if you can do that, then anytime you see mathematics playing a role in your physics, then you can just cash it in.
I don't think that's right about Field, right? So what Field says is, I can give you a story about the functional role of mathematics in terms of his, sorry, jelly is kicking in and words are failing me now, but in terms of his conservativeness, field conservativeness, right?
Yeah.
But what that what that tells you is, given a nominalistic formulation of physics, you can explain all the mathematical usages by restricting as quantifiers, adding math, and seeing if you get the thing entailed. But what it doesn't get you is that there is a nominalistic representation of physics. And so this is, like, all of this is sort of, if I was trying to do Field's project, which is very close to thinking of doing, this is all on the side of doing the, like, what is it to give the nominalistic subtheory of physics, right? Because if there's not one of those, then Field's in trouble.
Okay, that's helpful. So the story is you want to do all the nominalizing physics without quantifying over numbers, but you think you can do that with these ratios that you get, if I'm reading you right, by doing the holistic thing about the role of all the laws.
I didn't say that at first because I thought it was maybe a bit of a side thing, but I didn't think that I was committed to the holism that you suggested.
Well, here's
I wasn't quite
what I
sure
mean by that. I mean, I thought it was just following from the fact that you agree that if you just gave assigned numbers according to the first page story about what masses are, you're going to get it wrong. You have to relate them to other things in a way that satisfies the gravitational constant. That's what I mean by holism.
So I was thinking you can just give the first page story about numbers, but you haven't yet given the laws. When you give the laws, you add in that there is a relation. You discover a number that goes with that relation by doing experiments and stuff, but that's kind of order of discovery stuff. But sort of what it is to be the mass that it is not like dependent on what the gravitational relation is doing.
That just doesn't seem right. But I mean, the characterization of mass is not atomistic like that. I mean, anyway, okay, that goes.
I'm not sure when you say that. I don't know if you mean on my view or like it's a bad view of science.
Yeah,
I mean, that's a different issue. I don't want
to. The physics. I'm not an expert on this, but it seems to me that the mass is characterized in the context of all the laws.
I was thinking more atomistically, but I don't particularly want to battle that out right now. I mean,
okay.
I see it could go either way on that.
I'm sorry, I'm talking too much. No, thank you very much. That's helpful to understand.
Yeah, I'm sorry that wasn't clear. I should have made that clear.
Kirk, you got a follow-up?
Yeah, so you're you sort of want to vindicate the idea that numbers enter into the picture because they're helpful in capturing structures that they're independently, right? And we can prove a representational theorem. And it is true all these quantities appear in really complex theory relating to lots of other quantities. So in the case of the relations that are going to characterize the structure of the relations among masses, that's going to get characterized in certain terms operationally of some procedures for ordering masses, for example.
I mean, it typically does.
Yeah.
I don't know. That's.
Has that physical content in some way. Maybe
I don't really want to commit to that, but I'm happy to spot it for a moment.
Well, okay. I mean, for example, temperatures, right? There's a physical meaning to absolute zero on the Kelvin scale. There's a physical meaning to zero on the Fahrenheit or the centigrade scale. There's a physical meaning to the ordering as well. And then that gives out somewhere short of the full structure of the numbers, and so there are different ways of mapping the numbers on. So you'd think similarly in the case of masses, we're going to have some story about the physical meaning of the ordering relations and so on. And maybe in the case of masses, it turns out to be a simple story because of their interconnection with all the other laws, right? But so the ratios you're talking about also have physical meaning, right? Yeah. So that's so you say they got physical meaning, and that's what it comes to as a function in a certain way. And when you cast that out, you've answered, I think, Gary's question, which is what are the ratios in a way that doesn't involve any mathematics of the sort that would be forbidden here. Does that make any sense?
Not sure I quite tracked the last.
Yeah, well, just so the relations expressed by the ratios. Maybe I'll just ask a question here. Because, so are you thinking that's going to fall out of other things that are already in play?
Yeah.
Oh, I see. Okay, so
yeah. So
the meaning of the ratio is going to be given by more fundamental. Yeah. Got it.
Yeah, I mean,
so
I don't
that's
know.
Probably the bit that would.
Yeah, I guess we just looks like we're out of time. I mean, let me just briefly say why I didn't define this to defend myself a little bit. So there's a representation theorem. The way that understanding why a definition of this would work the way it's supposed to work kind of just pedagogically makes the most sense after you've understood how the representation theorem itself works. I was like, well, I would have to then, to define this, I would have to spend some time talking through the representation theorem. I was worried that would be a little bit too far afield.
Right.
I'm happy to chat about it kind of after, and if there's more time, I'm happy to go through it now. But I do think, look, I have a referee report, and it's exactly like, I don't know that that's going to do the job, and so I've got to do the same thing in the paper and kind of go through some more detail. And so all I'm doing now is apologizing for not having done that. That's kind of what the step is that has to be taken.
So I think that would actually address.
Okay.
That's what I was asking.
Okay.
about.
Okay.
Yeah.
I'm sorry.
I didn't do it very well.
No, I just didn't track. I apologize.
So I forgot to mention at the beginning that we have a reception, which I believe is just down the hall. So we can continue this conversation there, and maybe you can say some more about the representation theorem. So thank you so much.
Oh, thank you.
Make sure it's recorded.